to the code space. In the last first class, we have learned about the importance of synchronization. That is, synchronization is used to execute multiple processes without executing the critical section of processes at a time, avoiding the conflicts of data loss and data inconsistency. In this video, we're going to learn some synchronization algorithms by which we can achieve the synchronization among the processes. And first of all, synchronization is classified into three types. Synchronization using software, and second one is using hardware tools, and the third one is using OS based tools. And in software methods, we have lock variable algorithm and strict alternation, Peterson, and Decker's algorithm. And in hardware solution, we have TCL and swap algorithms, and the OS based tools will use sleep and wake up semaphores and monitors to achieve synchronization. Now, for a solution for a synchronization algorithm to be a solution for the synchronization, it should satisfy, it should guarantee these three things. First one is mutual exclusion. A solution must guarantee that at a time only one process can execute its critical section. Mutual exclusion. No two or more processes can enter into the critical section at a time. Only one process can only be able to execute its critical section at a time. And the second one is progress. The execution of a process of to be particular of an interested process does not affected by the uninterested process. The last one is bounded waiting. The algorithm should make sure that only the same process going the like it should prevent the algorithm should prevent the same process going into the critical section multiple times. So once a solution which satisfies all these three conditions, then it is said to be a complete solution for this synchronization. Now let us start about the software tools of achieving synchronization, in which we are going to discuss the first algorithm, that is lock variable. In this algorithm, we'll maintain a variable to make the entry section locked whenever a process is executing its critical section. The algorithm is simple, that will maintain a simple lock variable which is by defaultly 0, and will here will execute the non-critical section of that process, and then we'll write a while loop to make the process wait until the lock and until the critical section is locked, that is the value of lock is 1, and once the lock value becomes 0, the process enters into the critical section and it makes the lock value to 1 again, that is closing the entry section, and it will now execute its critical section and then open the entry section by making the lock value to 0. This is the algorithm of lock variable. Now let's check whether it is satisfying the conditions of a synchronization algorithm. First one is mutual exclusion. Like in this algorithm, if a process executing its critical section, like it is being executed by the CPU, gets preempted after this while loop and without making the lock variable to 1, then in that condition it enters into the critical section, but since it got preempted, it will allow the other processes to enter into the critical section, which means that mutual exclusion is not guaranteed. The second one is progress. We can clearly see that the algorithm can be executed even if there is no other process 2 in the ready queue. So the progress is guaranteed. Bounded waiting. If we check about the bounded waiting, here, if let's say the process 1 is being executed its critical section and leave the critical section, now again there is a chance that the process 1 can again enter into the critical section, blocking the other process, which makes the other processes starve. So for this algorithm, bounded waiting is not guaranteed. So we can clearly see that the lock variable is not a complete solution for this synchronization algorithm. So let's go to the next algorithm, that is strict alternation. In this algorithm, we'll maintain a turn variable with two variable values. The turn can be 0 or 1, which implies if the turn is 0, will allow the process 0 to enter into the critical section and performs its critical section. And once it performs completely its execution in the critical section, the turn variable will be changed to 1, making the process 2 to enter into the critical section. Here, will execute the non-critical section of that process. Then we'll check if it is the current process is process 0 and the turn is 1, then we'll make it in the waiting state. And once the turn value changes to 0, it will break the while loop and starts executing its critical section. And once it executes, it will again change the turn value to 1, allowing the other process to execute its critical section. And if there is another process, it would be somehow like this process 1, and here the turn for that is 0, and this is how the strict alternation works. In this algorithm, let's check for the mutual exclusion. Here, mutual exclusion is guaranteed since we can clearly see that once a critical section of a process is being executed, no two, no other process can enter into the critical section since the turn variable is not at changed. The and it maintains the ID of that process. It only allows the process with the same ID, and a process with an ID, the ID of the process is unique, so it does not allow any other process to enter into the critical section. It means mutual exclusion is guaranteed. The second one is progress. Let's check whether the progress is guaranteed or not. Now, let's say there is no other process interested to critical section. It means if there is no process, but the turn value is already 1, then we can clearly see that the process 1 will stop at this while loop and this while loop is not going to terminate. So, which implies that progress is not guaranteed. It can't move forward to execute its critical section. Progress is not guaranteed. Bounded waiting. Let's check for the bounded waiting. We can clearly see that a process which completes its critical section just now, then the turn value changes to the other process, making the current process preventing the current process from entering into the critical section. It means a process can't enter into the critical section repeatedly. It means that the bounded waiting is also guaranteed. We are successfully able to overcome these two problems of mutual exclusion and bounded waiting, but here in this case, the progress is not guaranteed. So, to overcome this, we came across the other two algorithms. One is the Peterson and the Decker's algorithm. We'll see in the next class. Let's compare these two algorithms, log variable and strict alternation. First of all, mutual exclusion, progress, and bounded waiting. Log variable, the log variable does not guarantee mutual exclusion, but it guarantees progress and it does not guarantees bounded waiting. And whereas in the case of strict alternations, it guarantees mutual exclusion, it guarantees bounded waiting, but it fails to guarantee the progress, which means neither the lock variable nor the strict alternation is complete solution for this synchronization algorithm. So we'll overcome these problems and we come across the other two algorithms, that is the Peterson algorithm and the Decker's algorithm. These are the correct solutions for the synchronization algorithm, which we are going to discuss in the next class. I hope you like this video. Thank you for watching.